Every second, thousands of tons of water plunge from hundreds of meters high to generate enough energy to power an entire city. But strangely, water contains no electricity. So what really happens inside a hydroelectric power plant? How can the movement of water be transformed into billions of watts of electricity, then transmitted hundreds of kilometers to every home? Today, we'll follow a single drop of water to explore its entire journey, from the reservoir at the top of the dam to the moment it becomes the electricity flowing through your home's electrical outlet. Humans have known how to harness the power of water for thousands of years. The first water wheels were used to grind grain, saw wood, and operate mechanical workshops. However, it wasn't until the late 19th century, with the invention of the electric generator, that humans discovered how to convert the movement of water into electricity, marking the beginning of the development of modern hydroelectric power plants. Today, hydroelectric power provides approximately 16% of global electricity production. Most hydroelectric power plants operate on the same principle. Water is stored at a high elevation to create potential energy, which is then channeled through a turbine to rotate a generator before the electricity is fed into the national power grid. It may sound like a few simple steps, but behind it lies a highly precise engineering system. To understand this entire process, we begin with where the plant's energy is stored, the reservoir behind the dam. In reality, before the construction of hydroelectric power plants, this was just an ordinary river, where water flowed from the mountains downstream according to the laws of nature. If the water were allowed to continue flowing like that, it wouldn't be able to create enough pressure and stable flow to generate electricity on a large scale. Therefore, humans built giant dams across the river. The purpose of the dam wasn't to generate electricity, but to retain the water, forming a large reservoir behind it. When the water level is raised, a significant difference in elevation appears between the surface of the reservoir and the turbine location. This difference allows the water to accumulate a huge amount of potential energy, ready to be released whenever the power plant needs to generate electricity. You can visualize this with a simple example. A bucket of water placed on the ground and an identical bucket of water placed on a table both contain the same amount of water. But when the water is poured down, the bucket of water at a higher position will generate more force because the water has more distance to accelerate under the influence of gravity. In hydroelectric power, the difference between the water surface in the reservoir and the turbine is called the head. The larger the head, the higher the pressure and speed the water reaches when it is discharged. Therefore, with the same flow rate, a plant with a large head can usually generate more electricity than a plant with a low head. Of course, all that energy is still locked behind the dam. Only when the water intake gates are opened does the journey of converting water into electricity truly begin. Of course, reservoirs don't just appear out of nowhere. The first step is always to build a dam large enough to block the flow and control all the water behind it. The dam must be able to withstand the pressure of millions of tons of water behind it. Most hydroelectric power plants use gravity dams, a massive concrete structure with a very wide base designed so that its own weight counteracts the water pressure. Before construction, the surface layer of rock is removed to expose the bedrock, and then cracks are reinforced to create a sufficiently strong foundation for the entire structure. Millions of cubic meters of rock are quarried, crushed into aggregate, and mixed into concrete before being transported to the construction site. The dam body is not poured in one go, but is divided into many separate concrete blocks, constructed in thin layers, and incorporates an internal cooling system to prevent cracking due to heat during the hardening process. After many years of continuous construction, the dam is finally capable of blocking the river, forming a reservoir and storing energy for the entire hydroelectric power plant. After the reservoir has been formed, the next task is to transport that enormous volume of water to the power plant, where rotating turbines generate electricity with virtually no energy loss. That's why the plant uses massive pressure pipelines, or penstocks, connecting the reservoir to the turbine area. Depending on the size of the plant, each pipeline can be several kilometers long and have a diameter large enough for a truck to fit inside. But even more astonishing is the pressure they withstand. With water columns hundreds of meters high, the pressure inside the pipeline can reach tens of bars, equivalent to millions of newtons continuously pressing against the pipe walls. To withstand such enormous loads, penstocks are constructed from high-strength steel plates, approximately 6 centimeters thick. These steel plates are bent into circular shapes using rolling mills, then welded by robots through multiple layers and rigorously inspected before being transported to the construction site. Here, sections of pipe weighing tens of tons are welded together and secured inside the tunnel with concrete, creating a system robust enough to withstand the pressure of the water flow throughout decades of operation. But the pressurized pipeline itself doesn't generate electricity. Its role is to deliver all the potential energy accumulated in the reservoir to where it's needed at the highest possible speed and pressure. When the intake gate opens, the water begins to accelerate in the penstock and rushes down to the power plant. Within seconds, it strikes what is considered the heart of the entire system, the turbine. It is here that, for the first time, the energy of the water flow is converted into mechanical rotational motion, laying the groundwork for the subsequent stages of electricity generation. So, how does the turbine work? And why, simply by the flow of water, can it rotate with enough force to operate a generator weighing hundreds of tons? When high-pressure water rushes out of the pressure pipeline, it is directed into a turbine, the component responsible for converting the water's energy into rotational motion. The water flows over specially designed turbine blades, creating thrust that causes the entire turbine wheel to rotate continuously. The stronger the water flow, the more power the turbine generates. Depending on the conditions of each plant, engineers will choose the appropriate type of turbine. For dams with very high water heads, Pelton turbines use high-speed water jets to directly impact the buckets and create rotational motion. For areas with low water heads but high flow rates, Kaplan turbines with blades that can change their angle of inclination are more efficient. Meanwhile, Francis turbines are the most common type due to their ability to operate stably under various conditions. Despite their different designs, all turbines share a common task: converting the energy of the water flow into rotational motion of a steel shaft. And this rotational motion is transmitted directly to the generator, where mechanical energy is first converted into electrical energy. Generator, where electric current is generated. As you just saw, any type of turbine is directly connected to a generator. Therefore, as soon as the turbine starts rotating, this entire motion is also transmitted to the rotor, the rotating part at the center of the generator. The rotor carries extremely powerful electromagnets. As the rotor rotates inside the stator, the stationary part is wound with thousands of turns of copper wire, and the magnetic field around the coils constantly changes. It is this change in magnetic field that causes the electrons in the copper wire to begin moving, creating an electric current. This principle was discovered by scientist Michael Faraday in 1831 and remains the foundation of most generators worldwide today. From hydroelectric and thermal power to wind power. By this point, the water's energy has completed almost the entire transformation process, from potential energy in the reservoir to kinetic energy of the flow, then to mechanical energy of the turbine, and finally to electrical energy. However, the electricity just generated cannot yet be transmitted far. Before being integrated into the national power grid, it must pass through another crucial device, the transformer. If electricity is fed directly into the power lines, a significant portion of the energy is lost as heat due to the resistance of the conductors. To minimize this loss, the current is first passed through a transformer. This device increases the voltage from the few tens of kilovolts generated by the generator to very high voltages such as 110, 220, or 500 kilovolts, depending on the transmission system of each country. Increasing the voltage reduces the current intensity in the lines, thereby significantly reducing the amount of energy lost during transmission. As a result, electricity can be transported hundreds, even thousands of kilometers, from power plants to residential and industrial areas with high efficiency. However, these hundreds of kilovolts are too dangerous for everyday use. Therefore, before reaching household appliances, it must pass through several other transformer stages to reduce it to a safe level. From the high-voltage transmission system, the electricity continues through intermediate substations to gradually lower voltage levels before being distributed to each residential area. Finally, at local substations, the electricity is reduced to approximately 220 volts and then distributed through the network to factories, offices, and individual households. Only at this point does the electricity generated from the movement of water truly become a source of energy for daily life. And so, you've learned about the entire process of electricity generation from a hydroelectric power plant to your home. This content is quite extensive, and I used many simulations because electricity is invisible, so if you have any questions, please let me know. Now, goodbye, and see you in the next videos.